Would it be like a polyatomic ion or polyatomic molecule?
Yeah, no, if it lets you do it, they're still available. Yeah, so they should be available up until 8. So, sorry about that. So if we have something like this, yeah. What does this mean? It means there's 3 aluminum?
No, 3 of the polyatomic ion.
This.
Uh,
Oh, so 3 of the perchlorate. Okay, so there's 3 of the perchlorate. So that basically means that there's 3 of what's inside of there. Okay, so everybody remember that? Okay, good. So if we are trying to get a tally of all of the elements, how many aluminum do we have here?
1.
So we'd have 1 aluminum. How many chlorines do we have? 3 chlorines. Chapter 7. Am I on the wrong chapter? Is that what you're telling me? Okay. And how many oxygens?
12.
12. 12. Do you want to see how we got 12? Okay, because there's 4 in there, and we'll have 3 times of whatever that number is. Yeah. Okay. Okay. Okay, questions? You guys got it? Not too hard, nothing new, right? Everything that we've already done. Okay, so, on. There's something wrong here. Oh, that's right. How many atoms of each element are in the formula unit ammonium carbonate? So, ammonium carbonate. What is the chemical formula for ammonium carbonate? It's NH4. Okay, and
CO3.
CO3. Is that balanced completely?
No.
Okay, how do I balance it?
Carbonate has a 2 negative,
Okay,
and ammonium has a positive.
okay,
We would need 2 ammonium.
so I'll need 2 of these. Like this,
Yes.
okay? So, how many nitrogens do I have?
2.
How many hydrogens do I have?
8.
How many carbons?
3. Oh, 1. Sorry, 1.
1 carbon. How many oxygens?
3.
Okay, questions? Concerns? Okay, good. Okay, so when we talk about molecular mass and formula mass, there's a little bit that's distinguishing those two. So molecular mass refers to a molecule. And often when we think about a molecule, it's going to be a covalently bonded molecule, right? So for instance, let me give you an example of what I mean. So we know that carbon dioxide, if we drew the Lewis dot structure of carbon dioxide, who's going to be in the middle?
Carbon.
And we know that everybody's going to try to have 8 around, right?
Mm-hmm.
8 valence electrons around them. Okay, so we know that these electrons are being shared. So that's the whole concept of being covalent. Now this guy acts as a unit, right? They're acting together. They're going to be totally interacting together, right? So they act as one complete unit. Where if we take something like sodium chloride is going to be a little bit different, right? So sodium has what charge associated with it?
Plus.
It has a plus charge. And the chlorine
Negative.
has a negative charge. Okay, and they're going to be interacting with each other because of the charges of those electrostatic charges. So in other words, if this guy is a minus and this guy is a plus, then a plus could sit on top of it. A plus could sit on the bottom of it because this whole thing is a minus. Does that make sense? So have you guys ever played with magnets? And you can stack them up on each other, right? And then if you get them on opposite ends and they repel each other, right?
Mm-hmm.
Okay, so it's very much like that, okay? So when we talk about formula mass, it's making reference to just looking at sodium chloride and not all of the different stacking up, so that plus and minus, plus and minus, plus and minus that you're gonna have, right? Because that's what forms that lattice, is that different stacking up, where in the case of the molecular mass is making reference to that molecule. Now, the process of calculating its mass is going to be exactly the same. You just count how many of each element are going to be there. And then you multiply it by how much each weighs. So for instance, if we take a look at sodium chloride, sodium weighs how much?
$22.9.
So 22.9. So we could count around that up to 23. We have 1 sodium, so 1 times 22. Yep, because we're just rounding up, right? And then chlorine weighs how much?
35.
35?
35.
So, oh, go ahead. You said 35.45, right?
Mm-hmm.
And so the mass of that compound is going to be the sum of the two, right? There's 1 of each. So then that is 58.45. And the units would be AMU, standing for atomic mass units. That's a 58, yes.
So that would be the molecular mass,
That would be the formula mass.
formula mass. Okay.
Yeah. The process of calculating is going to be exactly the same. Only thing, molecular mass pertains to things that are covalently bonded, and then formula mass pertains to things that are ionically bonded. Yes. chapter 7. This is chapter 7. Yeah, but I also have chapter 8. We haven't done it yet. I'll have that to you later. So in your book, often you'll see mass units, or you'll see MUs for mass units, or you'll see units. So you'll kind of see all three sources: AMU, mass units, units. They all mean the same. Okay, so if I was calculating the molecular mass of carbon dioxide, how would I go about doing that? Okay, so how many carbons do we have? Carbon?
1.
We have 1 carbon. Okay, carbon weighs
12.011.
Okay, so we can just round it up to 12. Okay, and then oxygen. How many oxygens do I have?
2.
I have 4. I have 2. Okay. You guys are trying to keep me on my toes today, huh? Okay. Okay. So in that case, the mass of oxygen is 16. Yep.
Yes.
16. So it's 15.999 something, right? So 16 times 2,
32.
32, plus 12,
48. No, 44.
so it's 44 AMU. AMU standing for atomic mass units. What was that? No, atomic mass number is different. Yeah. Atomic mass number is you're making reference to the mass number. It's different, remember? Yeah. Than the, yeah. Are you want it to be harder? Is that what you're telling me? Oh, I'll make it harder. Don't worry about it.
So the molecular mass would be just like if there's one of each element, like an ionic,
Okay.
separate.
So yeah, so if it's an ionic compound, it's going to be the formula mass. If it's a covalent compound, it's going to be the molecular mass.
Okay.
Okay. Ionic compound, it's often referred to as formula mass. And if it's a covalent compound, it's referred to as molecular mass. Now, ionic compound is formula. Covalent compound is molecular mass. Okay. So now, for most of you guys care less about it because it's the same process of doing both, right? At the end of the day, you're determining the mass of the compound. That's what it boils down to. Okay. So, but for those who are going to go into chemistry, you have to be able to distinguish between them. But you'll notice that in your book, you'll notice, well, don't worry about it. You know, you say that now, but by the end of the semester, you're going to be like, oh my God, I really love chemistry. It's my favorite course ever. That's because it's making you work. That's all, you know. Okay, so okay. So this is just basically showing you that, right? So here, this is carbon. Here, this is oxygen. The fact that they're sharing, we're going to be determining its molecular mass. Okay. And so we know that carbon is 12.01. Oxygen is 16.0. There's 2 oxygens, so it adds up to 44 units. Okay, calculate the formula mass for ammonium nitrate. So first thing I need to do is to do what?
Write out sorry, I drew a blank.
Chemical formula?
Chemical formula, yes.
Okay, so we need to write out the chemical formula. Okay, so what is the chemical formula?
NH4 for ammonium.
NH4, and you said NO3 for nitrate. Okay. Good job. I can see somebody did really well on the naming part there. Okay, so how many nitrogens do I have?
1.
I hear 2 and I hear 1. I have 2, okay. Yeah. So I have 2 nitrogens. Nitrogen weighs, okay, 14 times 2. How many hydrogens do I have?
4.
And hydrogen weighs 1 times 4. Okay. How many oxygens?
3.
Oxygen weighs 16 times 3. Was that? It's 80. Okay. Oops. No, you're right. 16 plus 60 is going to be plus 4. It's going to be 80. Yeah, atomic mass units. No, usually it's lowercase, all lowercase. Yeah. Or you could put MU for mass units. That'll work too. Sometimes you even be lazy and just put units like they did the last slide. So, okay, long as you have units, right? Okay, so now the thing is that I don't know about you guys, but my eyes are getting worse and worse and worse. And I know I can't see a single molecule or a single compound. Okay. So, and I don't know anybody who can actually see a single molecule or see a single compound, right? Because if you can, let me know so I can make a lot of money off of you, you know? So, because we can do some incredible things, let me tell you. So, we have to get a type of unit that can allow us to manipulate it, right? Because you can't sit there and manipulate a single atom or a single compound. It's really hard to do. We often will use scales and things like that. So what we have to do is get another form of measurement, that's going to be comparable. That's going to allow us to do that. Okay. And that other form is going to be on the same scale that you guys have on your periodic table. The only thing is that you're going to be using grams per mole. Okay. So we're going to scale up, right? And so when we scale up, instead of using AMU, because AMU stands for just that single compound, right? We're going to be talking about a lot of compounds, right? And so when we scale up, we're going to be using what we call grams per mole. G standing for grams, MOL standing for mole. Okay. Grams per mole. Okay. So when we calculate what we call the molar mass, because it's based upon the mole, it's going to be the same way that we're doing it. The only thing, instead of using AMU, we're just going to use grams per mole. Okay. It allows that scale up directly. And I'll explain why here in a second. Okay. Okay, so what is a mole? Okay, so before we talk about a mole, how many of you guys drink sangria? Sangria. No, not the soda. Wine with fruit. Okay, so that's my favorite summer drink, right? Sangria, right? So let me tell you, I make the best sangria, homemade, delicious, but almost homemade. So, okay, so do you guys want my recipe? Okay, you want some? No, so I'm giving you the recipe so when I come over to your house, you can have my favorite drink, right? So do you want white sangria or do you want red sangria? You guys want red? Okay. Okay, so this is how I start off with my sangria. You're going to take a fifth of vodka. You're going to pour it. Don't worry, you'll be okay. Trust me on this. After you have that first glass, you're good to go the rest of the night. Let me tell you, I promise you. So you're going to take a fifth of vodka. You start off with the fifth of vodka, right? Then we're going to add a bottle of wine. So you can pick your favorite red wine. You can use a Merlot. You can use a fruit wine. You know, I actually have right now I have a grape and a plum wine. They're both really deep red, but beautiful, right? Delicious, let me tell you. So you put the whole bottle of wine in there, okay? So then you're going to take 2 apples, 2 delicious red apples. You want it to be really sweet, right? Got to cut them all up, put them in there. So 2 apples, okay? You're going to take about 40 grapes. You're going to cut them in half. Get the red or the purple ones, the big fat gold grapes. Yeah, well, get the seeds out, kind of. You know, you don't want people to get seeds and choke on you, right? So you're going to take a small bag of blueberries. Now that small bag of blueberries is going to have approximately 50 blueberries. You got that? 50 blueberries, roughly. And you're just going to dump the whole bag. And you want them to be frozen, right? Because the frozen do a better job of cooling down our wine. And it also helps with the absorption of the alcohol in the fruit. And then you want to get a small bag of strawberries. So a small bag of strawberries is going to have about 20 strawberries, and you want to just cut them in half, put it in there. Then I throw in 2 plums, right? Because plums are really, really sweet. They add a lot of sweetness to it, right? And so my red sangria is really sweet. My white sangria is a little dry. But
How many plums?
2 plums. Okay. The last thing, it's a lot of fruit, right? And so you're going to have this big old pitcher that you're going to have to divide up and everything in there. But the last thing I put in there is, have you guys seen, they call them red peaches, right? Red peaches. So the meat on them is slightly red. So they have a really deep red color to them. And so if you get some red peaches, they usually sell them at the side of the road. And so it really depends. I like peaches. So it really depends on how you feel about peaches, but I typically put at least 2 in. If I'm feeling really frisky, I'll put 4 in, right? Okay. So, and then you just let it sit in the refrigerator overnight so that the alcohol gets all absorbed in, It is bomb. It is so bomb. Okay. Oh, it is delicious. When you taste it, you'll be like, oh my God, it is good. Okay, so now I'm gonna ask you a question. Now, everybody got that written down? No, you didn't get that written down? You guys are horrible note takers. I'm saying all this stuff. You're like, I'm gonna record it. I'm gonna get it off the recording later on, right? Okay, so I know not to come to your houses because you guys ain't gonna have my wine there. So, okay. So, at any point, did I say weigh something?
Did you say what?
Did I say weigh something?
Weigh
I
some.
didn't say weigh something at all, right? So when we look at a chemical equation, is that weight that we're looking at? Or is that quantity? Quantity. Oh, crap. So quantity. So we're looking at quantities, right? And so when we're looking at the chemical equations, we're actually looking at quantity, but we will often be using weight to get to those quantities, right? So the mole helps us get to that weight component, but it also helps us with quantity, okay? You guys know what a dozen is? A dozen is 12. 12 of what? 12 of whatever, right? So I could have 12 wives. I could have 12 husbands. I could have 12 kids. I could have 12 cars, right? So it could be a 12 of anything. So if I say I have a dozen of cars, you know how many cars I have, right? Well, that's the way the mole works, right? A mole, 1 mole is 6.022 times 10 to the 23rd. It's also called Avogadro's number. A lot of people will call it avocado's number because you remember an avocado, but Avogadro is kind of hard to remember, right? Okay, and it's spelled kind of close, right? Even though if you notice it's spelled 2 different ways, it really should be that O here, typo. Okay, so that number is what represents a mole. So if I told you I have a mole of wives, how many wives do I have? I said a mole, right? If I said a dozen, that means I have how many wives? Okay, now in mole, I have 6.022 times 10 to the 23rd, right? 1 mole is equal to 6.022 times 10 to the 23rd. And that could be of anything. It could be molecules, it could be atoms, it could be shoes, it could be underwear, it could be husbands, it could be wives, it could be girlfriends, it could be side pieces. You know, it could be anything you want, right? So that is the beauty of using that term. Very much like the dozen, right? Very much like the dozen. It just means 6.022 times 10 to the 23rd. So what was that? Of anything. That's right, of anything. Okay, so now I want you to think about this. Make it really hard. So if I offered to give you $3 trillion or give you a mole of pennies, which one would you take and why? You take the mole?
The $1 trillion.
You take the trillion. Okay.
Yeah.
Okay. Yeah, but you know, come on, we're greedy now. Now, let's be realistic. We always want more, right? I mean, that, you know.
Can we do the conversion?
Sure, but I want you guys to give me your answer before we do the conversion.
It's easier to carry the dollars than the pennies.
Well, if you have that many pennies, I'm sure you can get somebody to carry it for you. I'm sure they wouldn't be apt to say no, you know, because you can get it transferred over to dollar bills, right? So let's do the math, right? Okay, so we know a trillion is. So a trillion is going to be roughly, I think it's 10 to the 12th, right? Something like that. Okay, so, and then 6.022 times 10 to the 23rd pennies. Okay, so how many pennies equal $1?
100.
So $1 equals 100 pennies. So my answer is going to be 6.022 times 10 to the 21st dollars. Okay, now which one is more? 10 to the 12th or 6.022 times 10 to the 21st? Okay, good job. You know, when it comes to money, he knows his money there. Okay, so that kind of gives us an idea how much that is, right? That's a shitload of molecules, right? So if you have a mole of molecules, that is a lot of molecules. So for instance, 12 grams of carbon is going to equal 1 mole, right? 12 grams of carbon is going to equal 1 mole. Our periodic table, the mass on the periodic table is based upon that 12 grams of carbon, right? Equaling 1 mole. And so they literally count how many molecules are in that 12 grams. And that's how they got that number, 6.022 times 10 to the 23rd. Everything else is going to be based upon it, okay? So let's see how we can use the mole. What was that?
Just to clarify, so one carbon atom is 12 grams, and
No,
What?
not one carbon atom. One carbon atom weighs 12 AMU.
AMU, okay.
6.022 times 10 to the 23rd carbon atoms weigh 12 grams.
Okay,
Does that make sense?
yes.
Because we're saying let's say.
So would 1 mole of nitrogen atoms be 14 grams?
That's right. So one mole of nitrogen atoms is going to be 14 grams. That is
Okay.
correct.
Got it.
Yes, because 12, if you look at the periodic table, carbon weighs 12. It's 12 grams per mole, or 1 mole. Okay. So nitrogen is 14. So then that's going to weigh 14 grams for 1 mole. Okay. Okay, so let's say we have a sample that consists of 0.25 moles of ammonia. How many ammonia molecules is that? So how would I go about converting? So if I do conversions, this reminds me back in the day, chapter 3, you guys remember chapter 3 when we were doing all those conversions?
Yes.
Exactly, a little table thing I did. So I'm always going to start with what?
The given.
My given. I'm going to start off with my given. Okay, so here we have 0.25 moles of ammonia. What is the chemical symbol for ammonia?
NH4. No, NH3.
NH3. That's right. Okay, moles are on top. I want to get rid of moles and I want molecules. So what needs to be on the bottom?
1 mole
1 mole.
equals
And how many molecules are in 1 mole?
the 6.022 times 10 to the 20.
6.022
times 10 to the 23rd.
times 10 to the 23rd. And we don't want to mistake moles for molecules. They're not the same, right? Moles is that quantity, right? Molecules are just a molecule. So moles are going to cancel out. How many sig figs should I have? 2.
2.
2 sig figs. 1, 2. Right. So anytime you're using a conversion, right? This is considered a conversion. You never pay attention to the number of sig figs it has. You just pay attention to what you're given, what you're starting off with. So that's going to be 1.5 times 10 to the
23rd.
23rd molecules. Then H3. Okay. Questions? Yeah, so normally what I do is I multiply across the top and then I divide by what's on the bottom. That's what I do. Yes. That's what you're asking? Yeah. Okay. So we've already talked about the molar mass, grams per mole. So the molar mass allows us to sit there and go from quantity to mass. So we take a look at like an apple, right? Apple is kind of big, and we take a look at a grape, right? So if we have 10 apples, are 10 apples going to weigh the same as 10 grapes, right? They're not. So that's the same thing with the elements. They're going to be weighing different, right? Regardless of how much you have, they're going to have different weights associated with it. And so we have to take that in consideration, right? But by knowing how many you have, you can calculate the weight, right? So calculate the mass of calcium fluoride. So, and I should say specifically the molar mass. So how would I go about doing that? First thing I need to do is to do what?
The chemical
I need the chemical formula. Okay, so what is the chemical formula of calcium fluoride?
CaF3.
F2, right? Because calcium is a 2+, right? So calcium weighs how much?
40.
Okay, and we have how many? So 1 times 40. And fluorine, we have how many? 2. And they weigh 19. And the units are going to be grams per mole. Okay, so the molar mass for calcium fluoride is 78 grams per mole. Straightforward? Okay. Let's say we had, say, sodium sulfate.
So the chemical formula would be Na, and for sulfate, it'd be SO4.
Okay, so it's NaSO4. Is that it?
No, the
You said 2 NAs?
mhm.
There's 2 NAs. Okay, so How many NAs we have? So we
2.
have 2 NAs. Na weighs, so 23. So 2 times 23. How many sulfurs do we have?
4. Oh, 1.
1, right? Okay, so sulfur weighs
32.
32. Okay, and oxygen, we have how many?
4.
And oxygen weighs
16. It'd be 142. G per mole.
okay. 142. Okay. Piece of cake so far? Yeah, not too hard.
Dr. Henry, just a clarification. You said that mole is not the same. It does not mean molecule.
Yes, MOL does not mean molecule. Mole represents quantity. It could be any quantity, like a dozen. A dozen means 12, right? And so when we talk about the mole, it makes reference to that quantity, where a molecule is a molecule, right? That's telling me what it is. Does that make sense?
Yes, thank you.
Okay, so this figure basically shows you a mole of different elements here. So this is the mole of iron. Here's a mole of aluminum. Here's a mole of mercury. This is a mole of nitrogen. This is a mole of sodium, and this is a mole of copper. The mole is going to weigh differently, right? So mole of iron is going to be 55.8 grams. Okay. A mole of mercury is going to be 200.6 grams. A mole of copper is going to be 63.55 grams. So it's kind of like when I was talking about, we could have the same quantity of apples and grapes, but they're going to weigh differently. Right?
Mhm.
Okay. And that's the same thing when we talk about compounds as well. They're also going to take up different volumes. Okay, so how can I use this? So you're carrying out a laboratory reaction that requires 0.0360 moles of barium chloride. How many grams of the compounds do you weigh out? So where am I going to start at? I'm going to start with my given. What is my given?
0.0360.
0.0360. And that's units of what?
Barium chloride.
Moles of barium chloride. What is the chemical formula for barium chloride?
Are together.
BaCl2. That is correct. John. Okay. So we're going from moles to mass to grams. So what do I need to calculate first? Because we're starting with moles, right? Do I want the quantity of them or do I want the mass of them? I want the mass. So what units do I need to get? Grams per what? Grams per mole, because I want to get rid of the mole. So how do I calculate my grams per mole or my molar mass?
Hello?
How many bariums do I have? I have one. Don't I know how much one barium weighs per mole, right? So wouldn't I use that information, right? So I have one barium and it weighs how much? Okay, 137.3. And then how many CLs do I have? I have 2 CLs, and each one weighs how much? 35.45 times 2.
So should we be rounding those numbers or no?
It depends. That's a good question, right? If you look at your periodic table, and you look at another periodic table, and you look at another periodic table, each periodic table will have a different set of numbers. I mean, it'll be roughly the same, but they'll round it to a different point, right? They won't always round it. So you have the flexibility of rounding. So you want to kind of use common sense when you're doing the rounding. So in this case, if we round, we're getting rid of that 0.45, right? But that can make it, it can have an impact on the mass. And so in that case, we don't want to round completely up. And that 137.3, well, that's 0.3. That could also add something, especially since this one is going to be 0.9, right? So if we add these together, 137.3.
208.2.
And that units are grams per mole. Now, grams per mole. We know when we talk about grams per mole, this is 208 grams per 1 mole. So I'm going to use that to get rid of my mole. How many moles do I have? I heard somebody say it over here.
Wait,
1, because it's 208 grams. Grams refers to that 208. And then the mole is 1 mole. So anytime you hear per mole or per hour or per, that means one of those, okay? So we have 1 mole on the bottom of the barium chloride. And then up top, 208.2 grams. So moles are going to cancel out. Multiply across. What do you guys get? You said 750? Okay. So since this should be 3 sig figs, I'm going to put 7.5 O times 10 to the second power. You said, did you say 1750? 750. Yeah. No, it's not 1750, it's 7. That's a big, I know my big old 7 now. Let me fix it. You try using track pads to write all the time. Finger gets sore after a while. Okay, so questions? Okay. I'm gonna move forward. Try a little bit more. Okay, so if we look at this, if we're given units, let's say molecules, atoms, underwear, right? We want to convert to moles, right? And then for moles, you're going to use the molar mass to convert it to grams. So you're going to use Avogadro's number to go from those units to moles. And then you're going to go for moles, you're going to use the molar mass to go to the next step. Okay, you guys with me so far? Can nod or no, I don't know what the hell you're talking about. Okay. Practice, couple, yeah. Okay, so this is just basically telling us exactly the same thing. So if we're given mass in grams, we're going to use the molar mass, and that's going to give us moles. If we have moles, we can use Avogadro's number to get the quantity. Okay, so let's do a problem. Determine the mass in grams of 3.02 times 10 to the 24th molecules of sulfur tetrafluoride. Where am I going to start at? My given. So 3.2 times 10 to the and that's molecules of what? And what is the chemical formula for sulfur tetrafluoride? SF4. Okay. So what am I going to do? Okay, so we could do that.
So it's
So we have one sulfur. Sulfur weighs 32 times 1. Okay, we have 4 fluorines. Fluorine weighs, so 19 times 4. What is that? (108 grams per mole). But I have molecules. So how am I going to cancel out my molecules? What am I going to have? You said 1 mole on top? What was that? Are you sure? Because this is a mole. This is a molecule. Are they the same units?
it'd be 1 mole over Avogadro's constant.
Oh, so 1 mole over Avogadro's number.
Or
Okay,
yes,
and that
number.
is what?
6.022 times 10 to the 23rd.
6.022 times 10 to the 23rd. And that's molecules.
And then you would have 51.058 grams over 1 mole.
Why would I have 51?
Or sorry,
89 or
108?
Yeah.
Okay. So I need 108. Yep. Okay, so 108 grams over 1 mole. That's going to equal. So moles are going to cancel out. Molecules are going to cancel out. And we're going to be left with just grams. So this is going to equal so I should have 2 sig figs. So it's 5.7 times 10 to the second power. And that's grams of SF4. Yes. I do have them all. It's right here at the bottom. Right? Because yeah, you split them up because it's grams per 1 mole. Yeah. Yeah. So then I can separate. Good question. Okay. Questions? Cash, Kool-Aid.
I have a question.
Yep.
Why is it 10 to the second power?
It's 10 to the second because the answer is actually 573. So 10 to the second would be the 100th spot.
Got it.
Because if it's 10 to the first power, it'd just be the 10th spot. So it's literally this. Because there's only 2 sig figs, I want to make sure that I'm clear that there's 2 sig figs. So then it's 1, 2, right? So I'm moving over the decimal point 2 spots. So then it would be 5.7 times 10 to the second power. Or you could have just said 570. Just 570, 570. Yeah. Okay. Okay, so our next topic, percent composition by mass. So percent composition by mass is when we're looking at the part over the whole. So for instance, if we're talking about calcium fluoride, we know that calcium fluoride is made up of calcium and 2 fluorides, right? So the part would be looking at just one of them. So in this case, let's say we're looking at just the fluoride. So we know that the fluoride weighed how much? 19. 19 times 2, because there's 2 of them, right? So that equals. And then the calcium, there's 1, and that was 40. Just say 40. So that's going to be 78 grams per mole. So if we want to just look at the fluoride, the percent fluoride and calcium fluoride, we just take that 38 and divide it by 78 and multiply by 100. And then that's going to give me my percent of fluoride in calcium fluoride. So what do you guys get? Okay. Okay, so if altogether the calcium and the fluoride adds up to 100%, then how much must be the calcium?
So do you have 100?
Whatever's left. So 100 minus
48.7.
it's 51.3. Or I could have did it the other way where I just put that 40 divided by 78 and multiply that by 100. Both ways should give me the same answer. Okay. Questions? No? Okay. Okay, you guys ready? I'm sorry, did you guys get that all down? Don't worry, I got a handout for you. I haven't forgotten about you completely. Okay, so calculate the percent composition by mass of aluminum sulfate. Okay, where are we going to start at?
The chemical formula.
We need the chemical formula, right? Okay. So let's see. So what is the chemical formula for aluminum sulfate?
Al2SO4.
Al2. Okay. Okay, because we know that sulfate has a -2 charge. We need 3 of those, which is going to be a total of -6. And then we know that aluminum is a +3, so we'll need 2 of those to balance out that -6. Okay. Okay, how many aluminums do I have?
2.
I have 2 aluminums. Aluminum weighs
27.
times 2. So it's going to equal 54. So how many sulfurs do I have?
3.
I have 3. So sulfur weighs,
32.
so 32 times 3.
96.
And oxygens, how many oxygens do I have?
12.
12. Oxygen weighs
16.
16 times 12.
192. That's 342. Grams per mole.
Okay, so if I want the percent of aluminum and aluminum sulfate, what am I going to do? So I'm going to use 54 because I have to take in account all the aluminums that are there. $342 times 100. Okay. What does that give me? 15 something, right? So you said 15.77.
I got 15.78.
Okay. Okay, if I want the sulfur, if I wanted to get the sulfur, what do I need to do?
96 divided by 342 times 100.
So anybody else need chapter 11? And what do you guys get?
28.07.
So then oxygen, which should be the remaining, we could either just subtract the 2 by 100, or we could put the number in. Okay, what do you guys get?
56.14.
So 1, 2, 4. So if we're right, it should be 1, 3, right? Because then that's 10. Oh no, that's right. 1, 4, 1, 5 actually, right? Because they should add up to 100%.
How are we keeping track of sig figs throughout of all of this?
That
Are
is a
we-
good question. So in this case, because you're using just the numbers that are on the periodic table, you don't have to worry about sig figs. So what you decide to round it down to, if you decide to go to the tenths, or if you decide to go to the hundreds, that's up to you. Okay. Or in a question, it'll probably be specified to the 100th or to the 10th. Okay.
So it should be 56.15, right?
Okay. Okay. Questions? Concerns? Cash? Okay. Everybody got that down? What do you need a second?
So you can get to that last percentage just by having the 100 minus the 15.78 minus the 28.07.
That is correct. Yep.
You technically don't have to do that last equation.
That's right. Because 100%, that's the most that we can get, right?
Mhm.
At least right now. We'll talk about when that doesn't happen later on. Oh, you remember. Okay. Okay. Oh, sorry. Sorry, I erased. Do you have this lecture, by the way? You have this lecture? So. Yeah, check the. Okay, so another way that we can use the data that's provided. So if we have aluminum chlorate is 38.35% chloride. What is the mass of aluminum chlorate? I'm sorry, what mass of aluminum chlorate is needed as a source of 50.0 milligrams of chloride? I just made it sound that way. It's not that bad. Okay, so how would I start off with this?
A given.
My givens, right? Okay, so let's figure out what our givens are actually telling us. So if we know that we have 38.35%, so if we're talking about percentage, we always assume that's based upon the total amount, which is 100%. So if we assume that we had 38.35, and we just say milligrams to make things interesting, that means that I'm starting out with how many grams of aluminum chlorate? No, that's how much chloride I have.
61.5.
I'm starting out with 100, right? So that means that I'm starting out, my total is going to be 100 grams, right? So does that make sense? Okay, so I'm saying that I have 100 grams based upon this percentage, because we base everything on the percentage, right? So that means that 38.35 grams is going to be chloride, so that's going to be Cl, and this is going to be the aluminum chlorate. Okay. That's a 3. Yeah, this is a 3. You're talking about this one here? Yeah. That's a 3, yes. Are you making fun of my writing? Stop making fun of my 3rd grade handwriting. Is that better? Okay. So, or we could use milligrams if we wanted to, make it easier for ourselves. mg, mg. And the reason why we can use milligrams here instead of grams, or we can use grams, because the units are going to cancel out. Grams over grams is going to cancel out, right? So then that basically means that we have 50.0 milligrams of chloride on top, and X, that's what we're looking for, milligrams of aluminum Cl3. Okay. So I'm going to shift this up a little bit. Give us a little room to work here. Okay.
And then do you just cross multiply?
We're just going to cross multiply. That is correct. So I'm going to get X by itself. So I'm going to multiply both sides by X. Okay. So your X is going to cancel out. And then I want to get rid of this and bring it over to the other side. So if I'm going to do that, I'm going to multiply that by 100 over 38.35. Do the same thing over here. Okay, so then 100 is going to cancel out. 38.35 is going to cancel out. And then I'm left with just X is going to equal 50 milligrams of CO times 100 grams of AlClO3 divided by 38.35 milligrams of Cl. So milligrams of Cl are going to cancel out. And then I'm going to be left with my value. Did you guys get?
130.4 milligrams.
Okay, 366. So then it should be 1.03 times 10 to the second power milligrams. Okay. What was that? That's 38.35. Stop making fun of my third grade handwriting. I'm working on it. I'm working on it. So if you said 130, because there's technically 3 figs, 130 would only be 2. But if you said 130 point with the decimal point, that would be okay.
Is there, would we ever have to convert into a volume?
Yes, sometimes you will have to convert into a volume, but we're not there yet.
Okay.
Don't worry, we'll get there. And when we get there, then you'll have to rely on the density of things, right? Okay. Okay, can you repeat that one more time? Because we know that when we're talking about 100%, right? It's actually a fraction, right? So that would be that fraction of that amount. So we're saying that we're assuming that we have 100 grams of that product, whatever it is. And then that means that if I have 100 grams of that product, 38.35 is going to be Cl of that part. What was that? Okay, can you guys, wait. There's a question. Hold on. Okay, question. I need to be able to hear her and she needs to be able to hear me. If I can't hear her, I can't. Okay, so the question was, why are we multiplying both sides by 100 over 38? Well, we multiplied by 100 over 38 is to cancel out this so we can get x all by itself, right? So that's the reason why we do it. So we have to do that to both sides of the equations. But the reason why I chose 38.35 is because I made the assumption if I have 100 grams of the aluminum chlorate, then I know that 38.35 grams of it will be chloride, okay? And I know that because that's what that percentage represents, okay? So, and this is going to be important when we start trying to figure out empirical formulas, which is the next thing that we're going to be doing. Empirical formulas. Okay. Okay. How are you guys doing so far? Pretty good?
I need sangria.
Yeah, so I did it all in one line where most of the cases you did step by step. I did it all in one, right? On a single line. So all it is just trying to get rid of this so that I could get x by itself, right? Because right here, when we started out, we have over x, right? So we want to get x so it's all alone, right? So if we do that, we have to multiply both sides by x. That's what I did first. Then I multiplied both sides by 100 over 38 to cancel out the 38.35 over here and the 100 over here, right? But I have to do that to both sides. Okay, so what I do to one side, I got to do to the other. Okay. Okay. Yes. Because percentage, right? Because we're talking about mass first off. Okay, so really what we're looking at is the mass over the part over the mass of the whole when we're talking about the percentage, and we're just multiplying it by 100. Okay, since it's mass percent, I can make the assumption if I had 100 grams of aluminum chlorate, then 38.35 of it is going to be chloride, because that's what that percentage means. It says that 38.35%, if I assume that I had 100, it's going to be 38.35 of it is going to be chloride. So that means that the rest of it is going to be the aluminum. So, but altogether, it's going to be 100, right? Because that's what we're basing it on, 100%. Okay. So it's kind of like if I say that in this room, guys represent 5% of the class, right? And let's say there's 20 students in the class. How many students of them are guys? If guys represent 5 in the class. So if I said guys are 20% of the class, or did I say 5%? Well, 5% of the class. So if guys are 5% of the class, and then there are 20 people in the class, then how many guys do I have in the class? What was that? I would have 1, right? Okay. So, and how did you get to that? What was that? By my math. Okay, so let me take we're going to take a side step here. Let me get to another whiteboard. Hold on, whiteboard. Okay, can you guys see my screen? Okay, so I said that guys represent 5% of the class. Okay, so if we made the assumption that guys represent 5% of the class, right? So that means if I had 100 students, how many of them are going to be guys? 5, right? So that means that 5 of them are going to be guys. So we have 5 guys out of 100. Girls or whatever gender is left, right? So then that technically would mean that the remaining would be the other, right? But we had 100 total students, right? So that gives us our 5%. So then if I said that I had 20 students, but 5% of them are guys, so we divide this guy by 5, we divide this by 5, that'll give me my 20 students, right? And then that means that 1 guy in every 20 students. Okay, does that make sense? So we're doing something very similar to that, right? Okay. Okay. Okay, so percent composition, it allows us to sit there and get an idea of mass to mass ratios, right? Because we're talking about the mass of the part over the mass of the whole, right? You're with me so far, right? Good. Okay, so now how can we use this in other cases? So let's talk about the empirical formula. Okay. So first off, let's define what the empirical formula is. So the empirical formula is the lowest integral ratio of atoms to atoms in a compound. Okay. So in other words, we're going to divide it so that we can't divide it anymore by a whole number. Okay. So for instance, if we have C4H10, the empirical formula for this would be C2H5. Right? Because these are both divisible by 2. We divide it by 2, we get rid of that. And then we're left with just 2, 5. Okay. So, and we can't divide this by anything more and have a whole number. Right? Okay. So if I have C6H12O6, what would be the empirical formula for that?
C3.
CH2, right? Because they're all divisible by 6, right? So 6 divided by 6 will be 1. 12 divided by 6, that would be 2. And then O divided by 6 would be 1. Okay. You guys see that? Okay. What if I have, let's say we have you're dividing them by numbers that they're divisible by, right? Do you guys remember when you had the lowest common denominator, right? This is all it is. It's lowest common denominator, right? So what would you divide this guy by to get the lowest common denominator between these? You divide this by 6, right? Because these are all divisible by 6. It has to be, everything there has to be divisible by the same number, right? So if I have this, okay, this compound,
Divisible by 3.
it's all divisible by 3, right? So then that's P, that'll be C2,
H7.
H7,
And
Yeah.
then
right? So that would be the empirical formula for that. Does that make sense?
yes.
Okay, okay. Okay, so often what we're going to be given is mass, because when we do analysis, let's say forensic analysis, so a lot of times we'll inject a sample into the system and it'll come back and give us the mass of that sample. So it'll tell you it's this chemical and it was this much. And it was this chemical and it was this much, right? So then what we have to do is we have to go from mass to moles, because moles is quantity. And if we look at those numbers, we go back to these numbers, this tells me I have for every 4 carbons, there are 10 hydrogens, right? That's quantity, right? It's not mass. So we have to change our mass into moles to get quantities, and then we have to compare them to each other, okay? So let me give you an example of what I mean. A sample of pure compound is made up of 1.61 grams of phosphorus and 2.98 grams of fluoride. Find the empirical formula of the compound. Okay, so this is a mass. I need to get it to moles. How do I get it to moles? What was that? So then how do I get it to the units of moles? Well, because Avogadro's number, right? If we use Avogadro's number, that's molecules or atoms, right? But we have grams. So how do I go from grams to moles? I use my grams per mole. So then I use the atomic mass. What is the atomic mass of phosphorus? Okay, so then I'm going to divide this, it's grams, by 31 grams. And that's going to give me 1 mole, right? Okay, grams are going to cancel out. So I should have 3 sig figs, so that's 0.0519 moles. And then we have 2.98 grams of fluorine. So what do I need to divide that by? 19. 19 grams per 1 mole. Of fluorine. And so that's going to equal 0.157 moles. So at this point, we want to compare them to each other. So to compare them to each other, we want to divide it by the one that is the smallest. So we have 0.0519 moles, or we have 0.157 moles. Which one is smaller? So we divide both of them by that top number. So 0.0519. So that's going to equal 1. So we have 1 phosphorus. And then we divide this one by that same number, 0.05519. Okay. So we're going to end up with 3.2, right? But you're rounding it to a whole number. If this number is a 0 that follows it, you round it to a whole number. If it is a number like 2, 3, 4, 5, something like that, then we're going to have to do something a little bit different. And I'll show you that in a second. So in this case, we're going to round this up. So this is going to be approximately 3. So this tells me that I have, for every 1 phosphorus, I have 3 fluorides. Okay, so the empirical formula would be PF3. Okay, do you get that? No? Okay, so first thing that we wanted to do was convert to moles because we're talking about quantity. We know that moles represent quantity, right? So we know that, like in the case of water, tell me about water, H2O. What does that tell me? So for water, every time I have water, it's always going to be 2 hydrogens and 1 oxygen. Is that ever going to change? Right? So in the case of this compound, right, we're trying to get what we call the empirical formula, the simplest form of that formula, right? So we want to get that ratio between the two, right? But the only way that we can get that ratio is by getting the quantity first. Well, we got the number of moles, so we're comparing these moles. So by dividing both by the number of phosphorus, we're saying we're dividing it by itself. That's going to give me 1 phosphorus, right? And then we're comparing this. For every 1 phosphorus, I'm going to have, if I divide this tells me I'm going to have 3 fluorides. So always, that ratio is always going to be 1 to 3, right? So then my empirical formula is going to be PF2, like the ratio here is 2 to 1. right? Does that make sense? Okay, okay. So now, what happens if this number ends up being something like this? Hold on. Instead of this, oops. Instead of this here, it lets me write. I have 3.62 grams. Okay, so everything else is the same except down here. We're going to change that. Okay, so if we're starting out with 3.62,
.1905.
it's at 0.191. Okay, moles. So then that would give me 3.66. Okay, so this isn't close to a whole number, right? So if we have a number ending in 0.2, what can I multiply 0.2 by to make it a whole number? By 5, right? Because 5 times 0.2 would be 1, right? Okay, so if I have 0.25, what can I multiply that by to make it a whole number?
4.
Okay, if I have 0.33, what can I multiply that by to make it a whole number?
3.
3. And if I have 0.5, what can I multiply that by to make it a whole number?
2.
Okay, if I have 0.66,
You can't.
are you sure?
0.66.
Yeah, 0.66. Same thing as 2/3. So if I have 2/3, what can I multiply 2/3 by to make it a whole number?
Oh, it's reciprocal.
So 2/3, what can I multiply 2/3 by to make it a whole number? How can I get rid of the third? What would I multiply by?
You multiply by 3 halves.
Or multiply by 3, right? I don't have to multiply
Oh,
by 3 halves. I just multiply by 3 to get rid of the,
oh, okay. Got it.
okay? So if I have 0.75, sorry, points are not showing up well. 0.75, what do I need to multiply that by?
4.
4. And if I have 0.8, what would I multiply that by?
5.
5. Okay, so I have 3.67. So if I want to try to get that to a whole number, what do I need to multiply by? I need to multiply this by 3. So I multiply this by 3, and I multiply this by 3. So now this guy is going to be 3p, and then 3 times 3.67, if I remember correctly, that should equal about 11. Is that correct?
Mhm.
Okay, so then my empirical formula is going to be P3 F11. Okay, and we know that 11 isn't divisible by 3, right? It doesn't give us a whole number. Okay. Does that make sense?
Can we do an organic compound?
Yes, we can do an organic compound, but not yet. Give me a
Okay.
second. I have another example, which is an organic compound. Okay. Okay. So again, since we're talking about quantity, right? We know that we can't have 3.67 of a molecule of an atom, right? So for instance, let's say Heidi. I decide to cut Heidi in half. Is Heidi going to be okay if I cut her in half?
No.
No, right? Heidi is a whole person, right? If I cut her in half, she's dead, right? So that's the same thing that happens with an atom. If I cut an atom in half, that atom is no more, right? So I can't have 3.67 of an atom. So I need to find a way of getting it so it's a whole number. And we're talking about the empirical, the simplest form. So to get this to a whole number, I multiply this by 3, and that makes it 11. But I also have to do the same thing to the other atom as well, because they're in relative to each other. So what I do to one, I got to do to the other. Okay? Because they come as a package deal, right? So if I make this whole, I need to multiply this by that same number that I multiplied. Okay? Does that help? A little bit better? Okay. Let me give you another problem. So then it may help you. Okay? Everybody got this written down? Before I erase it. Okay, good. Okay, so here we have an organic compound. Okay, nicotine. How many smokers we got? Okay. So nicotine is 74.1% carbon, 8.64% hydrogen, and 17.3% nitrogen. Okay. So in this case, I have carbon, I have hydrogen, and I have nitrogen. Okay. So if I assume I had 100 grams of nicotine, how much of it would be carbon?
8.64.
74.1 grams is going to be carbon. How much of it is going to be hydrogen?
8.64.
8.64 is going to be hydrogen. And then how much of it is going to be nitrogen?
17.3.
17.3 grams. Okay. So how do I determine the number of moles? Because I got to get to the number of moles if I'm going to determine the empirical numbers, empirical formula. Sorry, can't even talk.
The mass.
The mass. So what is the mass of carbon?
12.01. So 12.
Okay, so 12. Okay. 4.1 divided by 12,
6.17.
6.1. 6.17, 3 sig figs, right? Moles. Okay.
And hydrogen, the mass is 1.
So the mass of hydrogen is 1 gram per mole.
So it's 8.64.
8.64 moles. And then nitrogen, 14 grams. Right in there. Okay, open.
1.24.
Okay, so which one is the smallest?
Nitrogen.
Nitrogen. Nitrogen is the smallest. So we're going to divide everything by the number of moles of nitrogen. .24. Okay, so let's do that math. So what are we getting for carbon? You said 5.02. So that's approximately 5. So we got 5 carbons. Okay. What are we getting for hydrogen?
6.97. So
6.97.
approximately 7.
So that's approximately 7.
And then 1 for nitrogen.
Okay. So then our chemical formula is going to be C5, H7.
And
That's right. Okay. Okay, that's how we would do an example with percentages. Okay, so any questions? Cash.
Oh, what would the formula name be? It would be pentacarbon
So it would
hepta
be,
hydrogen
so
nitride.
the empirical formula name would be pentacarbon hepta hydrogen nitride,
Okay.
or a mononitride. Yes. Yes. Why? Because you want to use the smallest number. You're using that as your reference because that's always going to be 1, your smallest one, right? So that's going to be your 1. And so it's all going to be based upon that. You always divide it by the smallest one. Okay.
Wait, I have a question.
Yes.
So I understood how to get the answer and everything, but how do we know which number to put? Like, how do we know which number to put under like the the mole. So for this first one was like 1 mole over the 12
The
grams. So like 3
the
mil.
1.24.
Oh no. On the first step. So
This
we got
here?
12 grams and then 1 gram and then 14 grams. Like how do I know to memorize which one
Because
to
you
put under the mole?
Okay, so it depends on the mass of the element. So how much does carbon weigh? You look on your periodic table,
Yeah, it's 12, right?
12. Yep.
Oh, okay.
So that's why we're going to divide by 12. We want to get rid of grams because we want moles. Right?
Oh, okay, cool.
Okay.
All right.
The empirical formula. That's it. No, if I asked you the name, then yeah. But in this case, you would just have to write the chemical formula. Right? Because it's asking for the formula. If they ask you for the name, then different. Okay. Okay, questions? No questions? Okay, good. So let's move forward. Okay, so if we're trying to find the empirical formula is that simplest form, right? But the molecular formula is the actual formula that we have. So to find the molecular formula, the first thing that you want to do is always find the empirical formula. If the empirical formula is given to you, then they're going to tell you, they're going to give you the molar mass of the compound, right? And then you use the molar mass to determine the molecular formula, okay? And the way you do that is you find the molar mass of the empirical formula, and then you're going to divide that by the molar mass of the molecular formula. I know you're all looking at me because you're like, that's a whole bunch of writing saying a whole bunch of stuff. Let's see it in action, right? So let's see it in action. Okay, so here is the empirical formula, right? C2H5. The first thing I want to do is find the molar mass of the empirical formula. So how would I find the molar mass of the empirical formula? C2H5.
So
Molar mass.
you have 2
50.
carbons,
I have 2 carbons.
and
Carbon
there's
weighs how much?
12,
12. So 2 times 12.
24.
Okay. I have
5 hydrogens, and
5 hydrogens. Each one weighs,
1.
sorry for cutting you off.
So it's 5.
Okay.
So the molar mass would be 29 AMU.
No, grams per mole, right? Or AMU, depending on what we're talking about. So we're talking about molar mass. Molar meaning for mole, mass meaning grams, right? So we want it grams per mole. Okay, so this is the molar mass of our compound. So it's 58.12 grams per mole. So if I divide this by the molar mass of our empirical formula, 29 grams per mole, correct? This is going to equal
2.
2, right? So the ratio of our molecule to our empirical formula, our molecular formula to our empirical formula is 2. So that means I multiply my empirical formula by 2. So C2H5 is going to be multiplied by 2. So then my C4H10.
H10. And that's the molecular formula.
And that would be the molecular formula. Okay, so the molecular formula is going to be a multiple of the empirical formula, right? Which makes sense, right? Okay, questions? No questions? Any concerns?
Can we do one more?
No, the molecular formula is a multiple of the empirical formula. So in other words, in this case, it's 2 times, right? It's twice the amount. By
So-
29, because that's the mass of the empirical formula. This is the molar mass of the molecular formula. Okay, yes. Oh, what? Okay, so I'll do one more problem. We'll pull it up from Chem 101. How about that? One of your homework problems. Is that fair? Okay. Let me find one. Yeah, this should be the one that's due this week. It was easy. Okay.
So is this a problem like a real life scenario, or is it purely like theoretical?
It's of course it's right now it's theoretical. We'll get to, you guys need a little bit more before we get to the real life scenarios, right? Don't worry, we'll get you there, I promise. It says, what is the molecular formula of a compound with an empirical formula of CH and a molar mass of 78.1 grams per mole? Okay, so what do I need to do?
The molecular mass for CH.
I need to find the molar mass of CH. So what is the molar mass of CH?
So carbon is 12
Okay.
and hydrogen is 1. So it's 13.
13 grams per mole.
So then you would divide 78.
So I have 78 divided by 13.
Equals 6.
So
So
would
then
that be C6H6?
So C6H6.
Mhm.
So you guys say D?
Yes.
Everybody say D? No? Yeah. Because this is 6, right?
1, 2. One, 2,
D?
6.
Okay. Okay. Piece of cake.
Yes.
Let me see if I can find one more challenging. What are you telling me?
How about 3,1 something or other bromo?
Okay. Okay, a compound containing sodium, carbon, and oxygen is found to have 1.06 moles of sodium, 0.528 moles of carbon, and 1.59 moles of oxygen. What is the empirical formula of this compound? You think it's C, but you don't remember? Okay.
So we'd find the molecule the mole mass.
Okay, so we have 1.06 moles of nitrogen. Of sodium. And then I have 0.528 moles of carbon. And then I have 1.59 moles of oxygen. Okay. So what do I need to do? Divided by the smallest, right? So you're right, divided by the smallest. So that's going to equal 1 for the carbon. 0.528. So we have 2 for sodium. 528.
Three.
Okay. So we get Na2, CO3. So you said D again? Anybody say D? Okay. Okay, let's see. Okay. Is it showing? Is the homework showing? Is it showing up now? The homework assignment? Yeah.
Oh, I haven't been seeing that on Canvas.
You're not
Is
seeing it
that-
on Canvas?
Yeah.
Okay.
On the calendar.
Yeah, I need to figure out what's going on. So the new company, I sent the message, they have not responded, so I'll call them tomorrow. Okay. Okay, so let's take a 5-minute break so we can shuffle my slides. So 5 minutes, go potty, do what you need to do, come back here and we'll start on chapter 8. Okay.
Dr. Henry?
Yep.
Is the Na2O3, is that a polyatomic ion? Or,
Na2O3.
yeah, or am I just, it looks like something like that ends in 8.
Yes, so this here would be sodium carbonate.
Carbonate. Oh, okay. So
Yeah, CO3, right?
okay.
That's carbonate. Yep.
I put the carbon in front, so I was very confused as to,
Yeah.
I
So
wrote
remember,
it
metal
incorrectly.
is going to go first, right?
Right. Thank you.
Okay, so let's see. Is everybody ready? Okay, chapter 8. You don't got chapter 8 packet? Anybody else read chapter 8? Everybody got chapter 8? Anybody need chapter 8? Good. Okay, so last week we were talking about reactions, right? So how do I know a chemical reaction has occurred?
A color change.
A color change, okay? Tell us.
Oh,
Odor.
fizzing?
Okay, so we have color change,
Temperature?
color, heat, okay?
Oh,
Odor,
sound and light.
light. That's a new one, sound, yeah, that's possible. Okay, what else? What was that? Well, that's a type of reaction. Don't worry about it, we'll get there. That's good though. She's like, really good. She's like, where's the extra credit, right? Okay, what else? What else? Flop, flop, fizz, fizz.
Oh,
what
gas.
It is gas formation, solid formation. Okay, so those are the ways that we kind of determine whether or not a chemical reaction has occurred, right? So let's go through this. So these are some of the evidence that we have a chemical reaction. So let me give you an example. So here we have potassium permanganate. Potassium permanganate actually turns purple when it's put into a aqueous solution. And then over time, it'll actually fade in its color, and then eventually it'll become clear over time as the ions separate.
Is that the temperature rising as well?
What was that?
Is that the temperature rising?
No, it's actually just the time. They're keeping track of the time.
Oh,
So
the
over time, the ions separate more and more. The more that they separate, it becomes clear.
Okay.
Okay. So we also have solid formation. So if we add sodium chloride solution and silver nitrate solution, we'll get a precipitant form. So we'll get formation of a solid. We could get gas formation in the case of Alka-Seltzer. You got Alka-Seltzer to water, fizz, fizz. You get carbon dioxide. We can have heat and light, right? Yeah, so if we get a sparkler, you know, you touch it, it's hot, right? Yeah, yep. We could have the glow stick, right? Right? So to get light emission, right? Okay. Okay, heat transfer. Heat transfer could be a chemical reaction as well as a physical reaction. So in this case, if we take ammonium nitrate and expose it to water, it actually sucks the heat from the environment. So you'll get cold. So the pack itself gets cold because we break up the substance that is holding the ammonium nitrate and allows the water to come in. Okay, so this cold pad gets cold as a result of that. Now, it's a chemical reaction, but it's also a physical reaction because you're getting that change in temperature, right? Okay, so help me out with constructing this chemical reaction. So I want you guys to help me write the chemical equation. It says, when solid sodium is added to liquid water, a reaction occurs, producing hydrogen gas and sodium hydroxide solution and heat. So
So is this our products and reactants?
So what are going to be my products? I mean, what are going to be my reactants? We'll start off with my reactants first.
Sodium.
Na plus, oh, sorry.
So we got Na. Is that a solid, liquid, gas, or aqueous?
Solid.
Solid. So what do I use to represent solid? S.
Subscript S.
That's right. S in parentheses. Okay. Plus H2O. Is that going to be a solid, liquid, or gas, or liquid? So I use the symbol L,
Mhm.
L for liquid. And then that's going to generate or yield what?
HG.
Sodium hydroxide. What is the chemical formula for sodium hydroxide?
NaOH.
NaOH. And it's a solution. So anytime that you see solution, we know that that's going to be aqueous. Yes, sir.
Plus H2.
Yeah, but it also means it's a solution as well, too, because acids are solutions, right? That's right. It's for both. Yeah. Okay. So anything else are we generating or making?
Hydrogen
Making
gas.
heat, and we're making hydrogen gas. So we'll have H2O and then heat. So often, if we know how much heat is generated, we can write it in terms of kilojoules. So we'll say plus so many kilojoules, like 486 kilojoules. H2O, I mean, sorry, H2O, H, and we know that that's a gas, so I forgot to put the G, right? G. H2, yes. Yeah, so if heat is being released, we put it on the other side of the reaction. I mean, or if heat is being released, it's on this side of the reaction. If heat is being inputted, we'd have to put it on the other side of the reaction. That's heat. Heat. Yes, plus heat. Sorry. Okay, is this balanced? No, it's not balanced. What do I need to do to balance it? So I have sodium. Somebody says, what else do I have?
Hydrogen.
I have oxygen and I have hydrogen. Okay, on my reactant side, how many sodiums do I have?
1.
On my product side, how many sodiums do I have?
1.
On my reactant sides, how many oxygens do I have?
1.
And on my product side, how many oxygens do I have?
1.
On my reactant side, how many hydrogens do I have?
2.
And on my product side, how many hydrogens do I have?
2.
I have 2 here. I have 1 here.
3.
I have 3. And this says heat. So don't mistake that for hydrogen. Yeah. Okay. Okay, so what do I need to do?
Multiply the hydrogen on the product side by 2.
Multiply this by 2. Just the hydrogen. Are you guys sure? Because right now this has 2. This guy has 1. So you're saying put a 2 in front of the sodium hydroxide? Okay. So if we put a 2 in front of the sodium hydroxide, we now have 2 sodiums. We have 2 oxygens. And we have 4 hydrogens. Now, what do I have on the other side? So if I put a 2 in front of H2O, so then that gives me 2 oxygens and 4 hydrogens.
And put a 2 in front of sodium.
And put a 2 in front of sodium. Okay, so that's 2 and 2, 2 and 2, 4 and 4. Are we balanced?
Yes.
Okay. Piece of cake? Okay, everybody got that down?
So we don't do anything with heat?
Yeah, well, heat is a little more complicated. We'll talk about that in 2 more lectures.
But for now, we just leave it.
Yeah, so you would just leave it as heat. That's why we just wrote heat, because we don't have a value.
So it's in the bond, right?
Yeah,
that
so
what-
the bonds, the fact that you have bonds breaking between the water molecules, so that's releasing that heat. Yes.
Okay.
Mhm.
Okay. So as we started, we first translated the chemicals, the chemical formulas, and we have to be sure that the chemical formulas are correct before we could actually start doing the coefficients. We know that sodium hydroxide was NaOH because sodium has a +1 charge and hydroxide has a -1 charge, so it has to balance out completely. Okay. So then after that, we start playing with the coefficients. And then we got the coefficients correct, right? Okay. And then, of course, we added our little symbols to let us know what those symbols are. Solid is an S, liquid is an L. It's a cursive L, okay? Gas is a G, and aqueous basically means dissolved in water. It's going to be AQ.
Do we need
Do's
to
and don'ts to,
oh,
go ahead.
sorry.
No, go ahead.
Do we need to know plasma at this point or no?
No, you don't need to
Okay.
know plasma at this point because typically plasma is not involved in too many chemical equations. Okay. So do's and don'ts to balancing chemical equations. Do's. The first thing that we always want to do is make sure that we have the chemical formula correct. Okay. The second thing that we want to do is that we want to use coefficients to balance out the chemical equations once those chemical formulas are correct. Don'ts. You don't want to make up stuff. So you're not just going to add something, and we're going to add water to this side and then water to the other side just to try to make it add up to what it needs to, right? You don't want to do that, okay? You want to actually put what's in the reaction. Okay, questions? So the other thing is that we never want to change. Once we have the chemical formula correct, we don't want to change those chemical formulas to try to make things add up. Okay. Okay, so we've already done this. Balance the equation for the reaction of solid phosphorus pentachloride with water, yielding the aqueous solution of phosphoric acid and hydrochloric acid.
So phosphorus is P.
So phosphorus is P. So it's phosphorus, solid phosphorus pentachloride. So that's one compound. So what is phosphorus pentachloride? PCl5. Solid, liquid, or gas?
Solid.
Okay. And
Perfect.
it's reacting with water. Chemical formula for water.
H2O.
Solid, liquid, or gas?
Liquid.
And that's going to yield phosphoric acid.
HPO3.
Are you sure? Are you sure it's that?
I'm going through the
H3
H. Okay.
and phosphoric. So if it's PO3, would that be Should be PO4. That's right.
Mhm.
Okay, solid, liquid, gas, or aqueous.
Aqueous.
And we have hydrochloric acid. HCl. Okay. And solid, liquid, gas, or aqueous. Okay. Is it balanced? Okay. So what do we need to do? Okay, so how many hydrogens do we have on our reactant side? We have 2. How many phosphorus? How many oxygen? And how many chlorine?
5.
Then on our product side,
4.
hydrogens, 1 phosphorus,
4.
4 oxygen, and how many chlorine?
1.
Okay, is that balanced? Okay. So what do I need to do to balance it? Where should we start? Put a 2 where? Over here? Did you say never mind or? Okay,
I'd put a 4 there.
put a 4 here because we have 4 oxygens, right?
Mm-hmm.
So that would give me my 4 oxygens.
And then that
How
would
many hydrogens do I have now?
be 8.
8. Okay, is that balanced?
No.
No.
I'd
Okay.
put multiply by 2 the 4 hydrogen.
Multiply what by 2?
Mm,
Do you put 5 in front of the as a coefficient for the hydrochloric acid?
So if I put a 5 here, okay, so if I put a 5 here, that will be 5 hydrogens plus 3 hydrogens. So that would be 8 hydrogens. And then that would be 5 chlorines. Okay, so that's 8 hydrogens, 1 phosphorus, 4 oxygens, 5 chlorines, 5 chlorines. So is that balanced?
yes.
Good job. Okay. Everybody got that down? Okay. Okay, so when we are interpreting the chemical equation, right? So at a particular level, it's really important that we don't have a fraction, right? But at a molar level, we can have a fraction, right? So that was that whole part about, I can't cut Heidi in half and she still will survive, right? So you're not going to have a half at a particular level. So in this case, for every 2 molecules of hydrogen, we need 1 molecule of oxygen to make 2 molecules of water. Okay? So here we can get away because it's at the molar level, right? Molar meaning that we have a whole bunch of them, right? So then we could have, for 1 mole of hydrogen, we'll need a half a mole of oxygen to make 1 mole of water. Okay. So what do I mean? So here we can see that there's 2 molecules of hydrogen gas, 1 molecule of oxygen gas. Okay, we're going to end up with 2 molecules of water. So if we had 2 dozen of hydrogen gas, then 1 dozen of oxygen gas is going to give me 2 dozen of water. So again, it's just based upon quantity, right? So I could have used dozens, or I could use just single molecules. Does that make sense? Yeah? No? Okay. So to writing and balancing chemical equations, the first thing that we want to do is try to classify the type of chemical equation that we have. You guys remember the different classifications? So if I told you I wanted a combination reaction, what is a combination reaction? Or a synthesis reaction?
A plus B yields AB.
So A plus B yields AB. Or in this case, we use A plus X yields AX. So this is an example of a synthesis reaction. Okay, where we get 2 or more substances to make a single product. An example, write the combination of solid aluminum and gaseous oxygen to form solid aluminum oxide. Okay, solid aluminum. What is the chemical formula for solid aluminum? Al
parentheses S.
parentheses S, that's right. Okay. And gaseous oxygen.
O2 parentheses G.
O2 parentheses G, that's right. Okay, and then we're making Al2O3. Solid, liquid, or gas?
Uh,
Is it balanced? Okay, what do I need to do to balance it? Okay, so we have 2 here, we have 1 here, we have 2 here, and 3 here. Is that balanced? Okay, what do I need to do to balance it?
So if you put a coefficient of 2 in front of the aluminum oxide.
So you're saying put a 2 here?
Yeah.
Everybody said 2 here? Okay, so then that gives me 4.
4 aluminum and 6 oxygen.
Okay, is it balanced now?
No. So then you go balance your oxygen on the reactant side by adding a 3,
Okay, so a 3 in front of there.
and then that gives you 6. And then you need to balance the aluminums.
By 4, you said?
Yeah, 4.
Okay, now is that balanced? Okay. Okay. Okay, so what would be an example of a decomposition reaction, since you talked about it earlier? Oh, you can't turn your head now. Decomposition. What does decomposition mean?
B.
AB yields A plus B.
Yeah.
Okay. So if we started with something that's together, so like A, B, and we're breaking it down to A plus B, right? Or breaking down, right? Entropy? No, it's not quite that. We'll have to talk about entropy later. And so not quite that. Okay, so but we'll talk about that. Okay. Yeah, those are examples. Yeah. Yeah. Well, metal rusting isn't. That's different because you're getting it's being oxidized. That's so different. Well, that's still you're still having a chemical reaction. That doesn't mean that you're decomposing it. Okay. So in this case, we have AX yields A plus X. Okay, so we get from one product to two products. Okay, so an example of this is water decomposing into its element when electrical energy is added. So what would be the chemical formula for this? Or chemical equation? So we have H2O. Is that solid, liquid, gas, or aqueous? It's liquid because it's pure water, right? Aqueous means that you're adding something in water. Yep. So you want to use L, okay? And it's decomposing.
H2
It's
plus
breaking down to its elements. What are the elements?
H2 plus O.
H2 plus O2. That's right, because we know that oxygen is diatomic, right?
Mhm.
Okay, is that solid, liquid, or gas? Gas. They're both gases, right, at room temperature? Because don't we breathe oxygen? Or do you guys take oxygen pellets? No? Okay. It's possible. Okay. Okay, so is that balanced?
No,
No. What do I need to do to balance? You said times hydrogen by 2 and times H2O by 2. Okay, so that will give me 4 hydrogens, 2 oxygens, 4 hydrogens, 2 oxygen. And everybody's happy. Okay. Everybody got it? Okay, so this reaction is a reversible reaction. What do I mean by a reversible reaction?
Oh, okay. So you can't have the double yield
Yes. So
arrows. Okay.
in the case of a reversible reaction, the way that we would signify something is going to be a reversible reaction or it's in equilibrium is that we have arrows going in both directions. Okay. So that basically means that we can get the formation of the elements and we can get the formation of water. Okay. So it's able to go in both situations. Okay. Okay. The last one that we're going to talk about today, and then we'll pick this back up on next Tuesday, but you're going to be here for lab on Thursday, right? Okay. So the last one is a single replacement reaction. So I like to say replacing the old girlfriend for the new girlfriend, right? Okay. So in that case, we're replacing B with A. Okay. So another name for this type of reaction is often called an oxidation reduction reaction. The reason why it's called an oxidation reduction reaction is because when something is oxidized, it's going to be losing an electron. When something is reduced, it's going to be gaining an electron. I'm going to show you an example real quick. Okay. But before I show you that example, when we do the replacement, we're going to have to replace a metal with a metal or with hydrogen, okay? Or we're going to replace a non-metal with non-metal. Yes, we did. So this is all review, right? Yeah. Good. Okay. So aren't you guys feeling like you know it now, right? Okay. Yeah, because you weren't here Thursday, right? So. Inferior. Okay. So if we have copper reacts with a solution of silver nitrate, we're going to get what?
Copper, nitrate, and silver.
Okay, so let's do it stepwise. So what would be the reactants?
Cu.
Is Cu. Is that going to be a solid, liquid, or gas? And then silver nitrate, AgNO3. Is that going to be solid, liquid, gas, or aqueous?
Yes.
How do I know it's aqueous? Because it's a solution, right? That's how I know it's aqueous. Okay, so what am I going to get as my product?
So
I'm going to
the-
switch Ag, so I'm going to get Ag by itself.
Wait, how did
That's
you
gonna
know it
be-
was a solution? Other than
Because-
maybe like you did photography.
What was that? Because it told us it's a solution.
Oh, okay.
Yeah.
Sorry. No,
That's all right.
I said photography because silver nitrate's used, I think, to,
Yeah, to develop film. Yep.
yeah.
Okay, so in this case, copper is always going to have a +2 charge. So in most cases, when you're exchanging a metal for a metal, they're going to end up with a +2 charge, except for silver. Silver is always going to be a +1. And aluminum is always going to be a +3. And cadmium is going to be a +1. But everything else is going to typically be a +2 charge. Okay, so we're going to end up with copper 2 nitrate. So if it's copper 2, how many nitrates will I need to balance it out? Are you sure?
Great.
What is the charge on nitrate? So it's a negative, right? Okay, so then I'm going to need, if it's copper 2, I'm going to need how many to balance it out? 2, right? So it's going to be NO3 with a subscript of 2. Okay, is that balanced? No. What do I need to do to balance it? Okay, how many coppers do I have? How many nitrates do I have? On the product side? 2.
One.
And then on the reactant side, 1. Okay. How many aluminum do I have? I mean, not aluminum, silver. How many silver do I have on the other side? 1. Okay, is that balanced?
No.
Okay. So what do I need to do to balance it?
Put a 2 on the reactant side of Ag, silver.
So on the reactant side, in front of, okay, so 2 here.
Mhm.
Okay, so then that would give me 2, and this will be 2,
And then a
Okay.
2 on the
and then a
product.
2 here. Okay. So is that balanced? Okay, that's it.